Look at zeros, multiplicities, the degree of a polynomial, and how it all relates to the appearance of the graph of a polynomial function. So let's look at the polynomial function p of x equals x plus 1 squared, x subtract 2. If we multiply it all out, it will be a third degree polynomial. X cubed subtract 3x subtract 2. You can get that by doing a lot of FOILing. So we know this is a third degree, which means an odd degree polynomial with a positive leading coefficient. We know its left-hand behavior. What happens as x approaches negative infinity will be decreasing. So as x approaches negative infinity, y is approaching negative infinity. And its right-hand behavior, what happens as x approaches positive infinity, is increasing. So as x approaches positive infinity, y is also approaching positive infinity. So I graph the function, and that looks correct. Now I want to focus on the x-intercepts. Notice that at x equal -1, the graph of the polynomial touches, so it is an x-intercept, but doesn't cross. We kind of say it bounces off the x-axis. Well, at x equals 2, the polynomial actually crosses the x-axis. Here's a couple more examples where the polynomials are in factored form, which makes it easy to spot the zeros in the x-intercepts. So x subtract 3 to the third power and x plus 2 squared. Notice that this one, where x is -2, we're just touching, we're bouncing off. And at the 0, x equal 3, the graph is passing through. And at this one, x plus 1, x subtract 2, x subtract 5 squared. For x plus 1, that gives us a 0, x equals -1, and it passes through. At x subtract 2, that gives us a 0, x equals +2, and it passes through. Where at x subtract 5 to the second power, that's one of the x-intercepts that bounces off the x-axis. So we want to focus on the relationship between the exponent on the factor, the zeros associated with that factor, I don't think I said that right, and whether the graph of the polynomial touches or crosses at that particular 0 x-intercept. So at x subtract 5, we had an even exponent and it touched. At x subtract 3, we had an odd exponent and it passed through. X plus 2 squared, we had an even exponent, it touched. X plus 1 has an understood exponent of 1, so it's odd, it passed through. X subtract 2 has an understood exponent of 1, which would be odd, and it passed through. So if a polynomial is written in the factored form, x subtract a to the power of m, x subtract b to the power of n, etc., we say a is a 0 of the polynomial with multiplicity m, and b is a 0 of the polynomial with multiplicity n. Graphically, if m is even, the graph will touch the x-axis at x equal a but not cross. It will bounce off the x-axis. Whereas if m is odd, the graph will cross the x-axis. So if the multiplicity is odd, the graph will cross. Going back to our examples. So again, x subtract 3 cubed, x plus 2 squared. 3 is a 0 with multiplicity 3, the exponent of 3. -2 is a 0 with multiplicity 2. Remember, these have to be in the form x subtract c, x subtract a, so this is x subtract -2. And so with the odd multiplicity, it passed through. With the even multiplicity, it bounced. And the total degree of this polynomial is going to be 5. If we were to multiply it all out, we'd have x to the 5th power. And the quick way to get that is by adding up the exponents. X plus 1, x subtract 2, x subtract 5 squared. So -1 is a 0, and we don't say it has any multiplicity because it has multiplicity 1, but then that wouldn't be a multiple, would it? So it's just -1 is a 0 without a multiplicity. It's only in there once. X subtract 2 means that 2 is a 0, and it's only in there once. And then x subtract 5 tells us 5 is a 0 with multiplicity 2 because it's in there twice. X subtract 5, x subtract 5. And again, matches up with the graph. If the multiplicity is odd, or multiplicity of 1, it passes through. Even multiplicity, it touches. And then the total degree of this polynomial is 4, which is an even degree with a positive leading coefficient of 1. And so the behavior of the graph looks correct. We are increasing here on the right, increasing here on the left. Okay, so let's take a look at this messy little guy. Here, it looks like the graph is touching and bouncing off. Here, the graph is passing through the x-axis. Here, the graph is passing through the x-axis. And then here, the graph is touching and bouncing off. So what might be the degree of this polynomial? It does look like it's an even degree because the right and left-hand behavior are both increasing. So at x equal -8, the degree has to be at least 2 because it's got an even multiplicity because it's bouncing off. But it could be 4, 6, 8, 22, 118, etc. At x equal -4, the graph's passing through, so it's got an odd multiplicity, so it's got to be at least 1, but it could be 3, 5, 13, 87, etc. At x equal 2, it's got to be an odd multiplicity because it's passing through, so it's got to be at least 1, but it could be 3, 5, etc. And then at x equal 5, it's got to be an even multiplicity, so it must be at least 2, but it could be 4, 6, 100, etc. And here's a concept, it's kind of jumping ahead, so kind of put this in the back of your memory and maybe come back to this for when you get to the Polynomial 2 quiz. Only real zeros are going to show up on the graph as x-intercepts. There could also be non-real zeros, such as 2 plus 3i or 3 subtract I. Any non-real zero will come in what we call conjugate pairs. If 2 plus 3i is a zero, then 2 subtract 3i would have to be a zero also. So a plus bi, a subtract bi, those are what we call conjugate pairs, which would mean non-real zeros would add 2 to the total degree of the polynomial. So what's the minimum degree of this possible polynomial? This has to be at least degree 2, at least degree 1, at least degree 1, at least degree 2. So the minimum degree this polynomial could have is degree 6. But it could also be degree 8, degree 10, degree 12, because if there's any more degrees, they always go up by an even amount. So this could be at least, must be at least degree 2, but could be 4, 6, etc. So adding 2 each time. Same thing with the odds. It's got to be at least 1 here, but could be 3, could be 5. So could add another 2, 4, 6, whatever to the degree of the polynomial. Any non-real zeros would add a degree 2 to the polynomial. So it's got to be at least degree 6, but it could be larger than that by an even number.